we'll get the introduction going. So, Dr. Ioannidis is a professor of medicine and a professor of epidemiology and population health at Stanford University. In addition, he holds professor positions of biomedical data science at the School of Medicine and statistics at the School of Humanities and Sciences. He is also the co-director of the Meta Research Innovation Center at Stanford. Dr. Ioannidis is a leading voice in the field of meta research, a field which studies research itself. His work aims to improve research methods and to enhance approaches to integrating information and generating reliable evidence. He is a physician scientist who completed his undergraduate and medical degrees in Athens, Greece, before coming to the US to complete his residency at Harvard Medical School, a fellowship at infectious diseases at Tufts University, and a doctorate in biopathology back at the University of Athens. Moreover, he is a highly cited researcher in both clinical medicine and social sciences, with over 1,200 publications, many of which are cited in very high impact journals. A reflection of this is an extraordinary H-index of over 245 over the course of his career, putting him among the most highly cited living scientists. He's held positions as a member of the executive board of the Genome Epidemiology Network and senior advisor on knowledge integration at NCI and NIH. He has served as president, Society for Research Synthesis Methodology, and editorial board member of many leading journals, as well as serving as editor-in-chief of the Medical Journal of Clinical Investigation. He is president-elect of the Association of American Physicians, the most prestigious honorific society for physician scientists. He has delivered over 700 invited and honorary lectures and has been a recipient of many awards, such as the Gordon Award for Epidemiology at NIH and the inaugural Howard Prize for Intellectual Courage. He's received many other honorary titles and doctorates from several universities. I could keep going, but I think this intro speaks for itself, and we're excited to hear what you have to share with us today, Dr. Ioannidis. So without further ado, the floor is yours.
Thank you very much. I'm greatly honored by the invitation. It's a very special honor to be selected by the graduate students as a speaker for your seminar. Let me see if I can share my screen for the slides that I have prepared. Can you see them now?
Yes.
Okay. So I will try to cover some empirical evidence and some thoughts on the issues of transparency, reproducibility, and usefulness in research. These three features are complementary. They may coexist, or sometimes just one of them may exist and may make our life difficult in trying to understand research, trust research, and eventually use research when it comes to medicine, public health, and other applications. My disclosures, no conflicts of interest other than the most serious one. I'm trying to be a scientist, which means that I'm probably unavoidably very biased. I'm sure that lots of my papers have lots of bias in them, and it's wonderful to hear what errors people can find in them and how some of these biases perhaps can be contained. Science is the best thing that can happen to humans, and I have no doubt that research needs to be supported with heightened commitments. It's our best window to the world and what we can do to improve our lives. But unfortunately, most scientific research to date has been non-reproducible and non-transparent. We mostly put trust without being able to really see the evidence. We read scientific papers, and there's about 200 million of them floating around. They're increasing at a rate of more than 5 million per year. But these are mostly advertisements. They're statements that some authors have done some research, and they're telling us that this is what they have done, and we need to trust it. But we don't see the data, we don't see the code, so we cannot really be sure. The question is also how much of that research produces useful evidence, because there's lots of incentives to publish, the classic publish or perish culture, But are these papers really useful? Are they really contributing to something that does change our life to a better outcome? This is some empirical data looking at how many papers over the last 30 years that have been indexed in PubMed Central and are open access have some features of openness that would help us improve our trust in them. For example, do they share data? And as you see, no country really has published a substantial share of papers among those that came with affiliation from that country that have that openness. How about registered protocols? Again, no country has a tradition of sharing protocols, of having registered protocols ahead of time for some work, for example, a clinical trial that is being published. Another feature of the scientific literature, which is very prominent across diverse scientific fields, but perhaps even more prominent in biomedicine, is that almost all papers claim to have statistically significant results. This is an empirical evaluation where we looked at the entire PubMed, both the abstracts that were there and any full text articles. Whenever p-values were used, 96% of the time, these p-values had statistically significant results in the abstract, and or similarly when we looked at full text articles. The proportion has gone down a little bit over time from 98% to 95% by the end of that survey, which we published in JAMA 7 years ago. We have repeated that exercise more recently. We've seen a further decline, but still the vast majority of the biomedical literature claims statistically significant results. So if someone wants to use statistical significance as a criterion for selecting what might be true or what might be correct, then this is not really the case. I see that there's a raised hand, so I'm wondering, should we take questions now or wait for the end?
We usually do it at the end.
At the end, okay. So the basic challenge is to separate how much of that literature is true versus not true, and also what we could do to make it more true and eventually also to make it more useful. And the utility aspect comes when we're dealing with research that does have some applied goals. It may not be relevant for research that is blue sky science, where we don't really know what even we're searching for and what may come forth. We don't know what the application of that knowledge may be eventually downstream. It could take 10, 20, 30 years sometimes, and that knowledge may be applied in fields that we don't really have a good sense when we start searching. But for most clinical research, and I would argue that that includes also public health research and epidemiology research, we do know that we have some goals, we have some deliverables. We want to improve human lives in terms of quality and also hopefully in terms of duration. Most clinical research and most public health research is not useful. And these are some features that would determine utility. Problem base. Is there a health problem that is big or important enough to fix? Context placement. Have we looked at what we already know? Have we systematically assessed prior evidence and therefore the need for doing yet another study? Information gain. How much are we going to change the entropy of the system? Are we proposing to do a study that is large and informative enough to really change what we already know, or solidify what we already know in ways that diminishes uncertainty in meaningful ways? Pragmatism, is that research reflecting real life, real people? And if it deviates because of some unavoidable artificiality that comes to almost any research design, does this matter? Can we transpose the research to the real life? Have we asked patients? Are we patient-centered? Do we care about what their priorities are? Researchers may have their priorities, patients may have their own different priorities. We have lots of great ideas, but we have limited funds, unfortunately. So is the research worth the money? Can the research be done? A lot of clinical studies need to be abandoned. About 40% of surgical trials, for example, never get materialized because of futility. They cannot enroll the patients that are required, even remotely, coming anywhere close to the intended sample size. And finally, transparency, which has multiple aspects. Can we really trust the methods, the data, the analysis? Are they verifiable? And if they're verifiable, are they unbiased so that we can put trust on them? If you look at across all the medical literature, most papers that are published do not fulfill any or just fulfill just a couple of these 8 features. If you decide to just read New England Journal of Medicine, JAMA, and Lancet, maybe they will do a bit better, but still most of these features would not be satisfied for the majority of the papers that are being published. And of course, you're missing then 99% of the fun, because most of the good papers are not going to be published necessarily in these few venues that publish only a very, very tiny fraction of the medical literature. Systematic reviews also can tell us a bit about the quality of the evidence. For example, the quality of randomized evidence that is directly linked to the guidelines and the decision-making process. This is some empirical exercise that we did a few years ago. We looked at close to 1,400 systematic reviews that were published by Cochrane, very respectable body of performing systematic reviews over a year and a half. We found that grades of recommendation, assessment, development, and evaluation, summary of findings had been done in only 44%. The remaining practically usually did not have evidence to be placed into perspective. And even when there was evidence and some assessment of that evidence had been performed at that high level, the quality of the evidence for the first listed outcome was high only 13.5% of the time. If we took all the outcomes that were listed, then 19.1% had at least one outcome with high quality of evidence. But if we asked for systematic reviews with high quality of evidence and statistically significant results and a favorable interpretation of the intervention by the systematic reviewers, we were down to only 25, which is less than 2% of the 1,400 topics that had been addressed in these reviews. We repeated that exercise recently, and we saw that there was really no improvement over time. There were some topics where systematic reviews that had been updated showed that we had a bit more evidence and better evidence. But in fact, there were other topics where we had realized in the interim that the evidence was not as good as we thought because new biases had been recognized in the meanwhile. When it comes to other types of research, like research that doesn't have pre-specified protocols, clinical trials hopefully are registered, at least this is what they're supposed to be. There should be a protocol. People have gone through IRB and they have vetted their intentions of what they want to study and why and what they want to measure. If we go to observational studies, then the degrees of freedom in getting results that may not be reliable increase dramatically. This is what I have described as the vibration of effects and Janus phenomenon. Vibration of effects means that in the same data set, for the very same question, you can get very different types of results depending on how exactly you analyze the data. And in fact, in many situations, there's different ways to analyze the data that you can get results that are exactly opposite in terms of their direction and what they mean. Janus was a Greek-Roman god who could see it had two faces pointing in opposite directions. These are data from NHANES, which is a very reliable representative survey of the US population. And if you look at the far right panels under D, these are 1 million analyses in that same data set trying to understand whether vitamin E levels, alpha tocopherol levels, are associated with the risk of death. How are we going to study that association? Well, we have to adjust for different things that may also affect mortality and which might be confounded with vitamin E. So we have lots of options. If we consider 19 different potential adjustments, throwing that adjustment in the model or keeping it out of the model is two choices, 19 variables, that is 2 to the 19th power, and this is about 1 million different analyses. 700,000 of these analyses suggest that vitamin E decreases the risk of death. 300,000 of these analyses suggest that vitamin E increases the risk of death. So unless we have a very clear plan of what we intended to do, we can get practically any result, and that could be reported, and a narrative can be built around it. Here's how that works in practice. If you look at the Boston Cookbook, which is just a traditional cookbook published since the 19th century. We took the latest iteration. We randomly selected 50 ingredients from that cookbook, and then we went to the scientific literature to see how many of them have scientific studies that are associating intake of that nutrient with cancer outcomes. And for 40 of them, we could find scientific studies that had looked at that association. The other 10 probably had studies, but we just didn't search with all the possible names that the nutrient could have. For example, we searched for vanilla, but we didn't search for vanillin, which would have found studies that were not retrieved with vanilla. Basically, for most of these nutrients, the results were all over the place. Some of these results were in the same direction. Nevertheless, for example, salt tended to be always on the bad side, and onions almost always, with one exception, were on the good side. But the magnitude of the effect sizes was completely all over the place. And based on what we know from the large, best conducted observational studies, like big, long-term longitudinal cohorts, the vast majority of these effect estimates are probably completely incompatible with reality. For example, we know that fruits and vegetables are good for your health, and probably they decrease the risk of cancer, but the best hazard ratio estimates are 0.999 or 0.998 per serving, which is something that would be almost indistinguishable from the vertical line at relative risk of 1 in that plot. If we look at the p-values or their equivalent, the z-scores, a z-score of less than -2 and more than 2 is nominally statistically significant, we see that in single nutrition studies, almost all the action is statistically significant results, as I showed you before. This is the green color. If we start looking at the papers more carefully for results that are hidden in some fine print, we find some more results that have not been highlighted, but some of them are non-significant. So we start filling in that middle gap of empty space in the non-significance region, but not much. If some of these nutrients do have an association with cancer risk, the fact that these studies are so small suggests that the vast majority of these investigations should have found statistically significant, non-significant results. So we should have seen a lot of action between -2 and 2, and very little action in less than -2 to 2. Meta-analysis might help a little bit because it may even the ground, and some of the extremes would cancel out. So a little bit of the middle space starts filling up, but not really much. So meta-analysis also cannot help if we have this kind of situation where every result is possible and every result can be reported. We can also look at specific topics to see how that operates. This is one of the most contested questions, for example, studies of alcohol consumption and breast cancer risk. There's some pattern of an association, but the question is, how big is that association? So we looked at what studies on that question have shown us, and I'm showing you here the minimum and the maximum effects in the same study. You can see that within the same study and what is reported, and of course there's many other analyses that are not reported, there's estimates that are completely in opposite direction and very different. So it depends on what one wants to highlight and where to place more attention. We get very different results when we have different exposure definitions, when we have different contrast levels, different study populations, different adjustment covariates, and different model approaches. Each one of these features is adding to the vibration of effects. I mentioned meta-analysis, and I do like meta-analysis because it tends to give a bird's eye view of the evidence, but meta-analysis cannot really do much if the evidence that it is built on is not very reliable. The superimposed problem is that we have just too many meta-analyses. We have an exponential, or at least geometric, growth in the number of systematic reviews and meta-analysis published over time. And if you look at them very carefully, most of them are not really useful. This is a very rough metapie of the production of meta-analysis. Some of them remain unpublished. Many of them are redundant and unnecessary. There's some topics that for some reason or other, people just keep publishing meta-analysis like crazy, and they just say the same thing, but it's just an easy target to do one more, but they're not really telling us anything new. Some are decent, but not really useful. You look at the question, you say, who cares about that? A lot is misleading, abandoned research topics like candidate gene genetics. Lots of studies in the candidate gene era, they're just out there, and people are creating meta-analysis of them, but we know that these are selectively published, and therefore the meta-analysis are likely to be flawed. They don't really agree with more thorough genome-wide associations. Many that are flawed beyond repair, there have obvious errors and flaws. And about 3%, this is my estimate, are both decent, well done, and clinically useful. So if one could isolate that 3%, then that would be nice. But even that is not easy, and it takes a lot of training and a lot of experience. So we want reproducible research, but what is reproducibility? All scientific fields are mentioning reproducibility of results or other terms like this, but there's no agreement on what that means, and people may mean different things. I would cluster reproducibility into three big areas: reproducibility of methods, results, and inferences. Reproducibility of methods is being able to understand what the method section says and put it to work, be able to repeat as exactly as possible the experimental procedures, the computational procedures. If it's a lab experiment, be able to repeat the lab experiment, and regardless of what the results would come out, but just getting the ingredients to work and piecing them together. Reproducibility of results is the ability to produce corroborating results in a new study, having followed the same experimental method. So if we can resurrect the methods, then we can try to recruit new participants or get new observations or new samples and run a similar study and see whether we get the same results. We know that in high-profile studies published in the top journals, this is very rarely feasible. For example, the Reproducibility Project Cancer Biology looked at creme de la creme, top-cited papers in cancer biology, and the vast majority of them, the experimenters could not even get the experiments to start because they couldn't understand what exactly had been done in these studies, and asking the authors did not really shed much light to this. Finally, we have the reproducibility of inferences, which is the making of knowledge claims of hopefully similar strength from some study results, which means that we have 2, 3, 5, 10, 50 different experts, and we ask them, what do you make of that body of evidence? And one might say, well, this intervention needs to be used in everyone, and another might say, no, it needs to be used only in the elderly, and a third one might say, no, it can be used above 30 years old, and another one might say, no, it shouldn't be used. And very often, with the same body of evidence, we have very discrepant interpretations. For example, mammography is a classic example. There's some people who say, based on the evidence, we have very strong evidence for widening the indications for mammography. Others say, no, the evidence says that it doesn't help at all. And everything in between. Here's some stereotypes. This is the stereotype of most research that is done in biomedicine and many other fields. Small data research. We have lots of smart people who want to do research, very limited funding. Each one of us can get a very small piece of the pie. Therefore, we run small sample size studies. We tend to be solo and siloed. We have to compete against other very smart people, and we need to show that we do the best work with sometimes very low acceptance rates for grant proposals and for success rates overall. This means that there's a lot of narrative building, cherry picking of the best looking results that can build the narrative for the next round of funding. A lot of that would be done post hoc. P-values of just less than 0.05 are considered to be enough. These are established in most scientific fields. No registration, especially in observational research, but sometimes even in experimental research. No data sharing and no replication, because if replication shows that our initially discovered signal does not hold up, then we're back to square zero, and we need to apologize that we haven't found anything, although this is completely legitimate. We've seen that pattern in many scientific fields. For example, we've empirically studied neuroscience, from basic science to translational science to clinical trials. The common denominator for all neuroscience research is that the average power of a study out there is about 20%, with pretty optimistic assumptions, probably 8%, 8.0% under more realistic assumptions. It's not just medicine. Economics is pretty much the same. Along with Tom Stanley and Krista Kouliagos, we have created an observatory of effect estimates in observational economics, with more than 70,000 effect estimates, we see a very similar pattern to what we see in neuroscience. These are fields that are very far apart, but power failure is a common denominator. Increasingly, we also have a second stereotype that is exactly the opposite. Big data science. We have electronic health records, we have genomic studies, we have all sorts of omics, we have new platforms that can collect personal information from mobiles and wearables, and we can get zillions of pieces of data. So the problem here is that now we are completely overpowered, and everything that we test will be nominally statistically significant. Again, one needs to build a narrative and cherry pick some results that would seem more promising. Most of that is done post hoc. There's far more fancy statistics being involved, and the problem here is that very often there's no consensus on what is the best statistical inference tools. Most of that research, again, is not registered. You see the darkness that I showed you earlier in the map of science across the world. And there is a bit more data sharing because many of these data sets may be available for others to use, but very often they're so complex that unless someone has spent a lot of effort to try to convey exactly how these variables were collected and what they mean and how they have been operationalized, then we're in deep trouble when we try to resurrect these data sets and use them if we're not familiar with what they're saying and what each variable is about. So big data, I think, has big potential, but also big potential for noise and also big potential for errors if not used properly. Finally, there's a third stereotype, which is becoming more common, especially in for-profit cycles that are also very influential in many research areas. I call that stealth research, and it means that data is not to be shared, protocols are not to be disclosed, it's all trade secrets, so we need to be in a stealth mode. And the classic example was Theranos. I wrote the first negative article against Theranos in 2014. It was published in JAMA after editorial, peer, and legal review, because at that time Theranos had the highest valuation than any startup in the US. It was considered to be the future of diagnostics and healthcare and everything. And I said, there's something clearly wrong here. The notion was that we should not disclose anything. We should not publish anything. They had no publication in the peer review literature. And obviously, that's not a good sign. They collapsed very quickly. Failed replication has been recognized as a big problem across many different fields. In fact, it is for-profit companies that led the way for empirical studies starting about 10 years ago. For example, this is a paper published in Nature Reviews Drug Discovery, where company people from Bayer said, all that research done in great universities does not work when we try to resurrect it and put it to use in our hands to try to develop new drug targets. How often does this happen? Where it's very, very dominant. Almost never can we replicate what these people at Harvard and Stanford are publishing. And Amgen did the same. Glenn Begley and his team published that in Nature in 2012. Only 6 of the 53 landmark studies for oncology drug target projects could be replicated. His conclusion was that the failure to win the war on cancer has been blamed on many factors, but recently a new culprit has emerged. Too many basic scientific discoveries are wrong. Questioned because he didn't release the open data, the raw data for these findings, but then independent efforts that were in public view and with full disclosures pretty much arrived at similar very low reproducibility levels. This leads to a lot of tension. We don't like to hear that our research is not reproducibility. It leads to some sort of war. It could be like a civil war within science. People are talking about that effort being successfully replicated or unsuccessfully or uninterpretable. Sometimes they have different opinions on whether it is replicated or not. And sometimes these discrepancies are very justified because it depends on how exactly you read the data. But basically, there is a lot of resistance to refutation. So if something cannot be replicated and we have given it the best possible shot, for example, you can take beta-carotene, where we had a paper published in Nature and other observational studies claiming that it will be the most effective chemopreventive agent for cancer. paper in Nature, cited thousands of times. And then we had 6 very large randomized trials showing absolutely no benefit. Well, the original Nature paper continues to be very heavily cited, and people still say that beta-carotene is going to be very effective as a preventive agent. I don't think we can spend more tens of millions of dollars in more randomized trials to refute that claim further. But once you have some claim out in the literature, it's very difficult to get it abandoned. We've seen that in very different fields, not just in medicine. We've seen it in psychology and the social sciences as well. Meta-analysis may have some use in telling us more about bias rather than effect sizes that are genuine. We can study patterns in the results of meta-analysis that are commensurate with the presence of different biases. For example, small study effect, when small studies give different results compared to large studies, or gray literature bias, when gray literature like theses give different results compared to publications in journals, or decline effect, when we see a big effect that is described in the first study, and then we see smaller and smaller or null effects in subsequent efforts, or early extremes. We see a big effect, it gets published in Nature, and then that's an opportunity for people to contradict it. They find a completely negative result, and then subsequent studies would show something in between. We probed these patterns of biases across about 300 studies in several thousands of meta-analysis, and we saw that most scientific fields have most of these biases, or at least hints or footprints of these biases in the literature. We also see examples where effects or associations or signals are there. It's not that they're completely false positives, but when they're discovered and when they make a big splash in the literature, they're far more prominent compared to what they probably really are. This is one such empirical evaluation where we looked at the most highly cited biomarker studies in the biomedical literature. And I'm showing you here the relative risk in the highly cited study that drove the field forward, and the relative risk in the largest study that probably is closest to the truth. I mean, we never know what the truth is exactly, but I mean, this seems to be like our best shot. Almost all the action is below the diagonal, meaning that the highly cited study that drove the field suggested a much stronger signal, a much stronger association compared to subsequent work. We see that also with more complex research. For example, we see it with multivariable models that are used to predict, for example, predict outcomes in cardiovascular surgery and other conditions. And we see that the original models that are proposed, or the original scores that use multiple variables, they tend to perform far better compared to subsequent efforts to validate the performance of these models. We also see that validations by the same authors who develop the scores tend to perform much better compared to validations that are done by external independent teams. How can we make things better? There's lots of things that are happening that are making things better. And I don't want you to get the sense that the biomedical literature is completely obsolete and we should just abandon it. These are recipes that have worked in different situations. Large-scale collaboration, adoption of replication culture, registration of studies, protocols, analysis codes, data sets, raw data and results, sharing of data, protocols, material software, and other tools, reproducibility practices, containment of conflicted sponsors and authors, more appropriate statistical methods, standardization of definitions and analysis, more stringent thresholds for claiming discoveries or successes, improvement of study design standards, improvements in peer review reporting and dissemination of research, and better training of the scientific workforce in methods and statistical literacy. I will describe a few of them to give you some empirical evidence about how they work or what are their limits and caveats. Sharing has gone a long way. I showed you these first slides, which might be a bit misleading because they covered 30 years of scientific publications. Yes, in 1990, very little was being shared. In 2023, a lot is being shared. And in fact, some fields, some domains, for example, genomics, have realized that the way to move forward is to share more, to be more open, to have the ability to verify results and also to use data very quickly. Just don't wait for someone to perform all the research and publish separately their own results. The teamwork, the community effort is much more important and much more influential, and that requires a lot of sharing. A few years ago, we published that paper in Science where we argued that there should be unrestricted use of genomic data in public view, especially when these are data that have been generated with taxpayer money. How about data that belong to past studies? Can we unearth them in different scientific fields? Along with Tom Hardwick, we have built the Data Arc, which is an effort to unearth and release in public view for public use all the data sets from the most highly cited papers in different scientific fields. And these are the results for the most highly cited papers in psychiatry and psychology. We sent requests to the authors of these papers, and we told them, we will curate your data for free. We will make them available for free. Just give us what you have, and we'll make them available for everyone. Some had already shared their data, and some more did share their data, but unfortunately, many could not. And the reason for this was that in many situations, the most common reason was that that was not within the researcher's control. In fact, in many of these highly cited papers, the primary investigators had never seen the raw data. These were, for example, industry-sponsored studies, and the biostatisticians at the industry had seen the data, then they sent the analysis to the principal investigator, but the investigator never saw the raw data, just put trust to the statistician that that should be okay. The International Committee of Medical Journal Editors has also asked for the last 5 years that there should be data statements in published papers, especially for studies like clinical trials. And this is, I think, a wonderful movement. It means that you need to say, what is the plan for sharing the data at some point, now or later? And we looked at New England Journal of Medicine, Lancet, and JAMA to see what happened with the first 500 trials that they had published. Yes, most of them had data sharing statements, but only slightly more than half of them would share their own data at some point. And then only 20% had clarified where that would be, in what repository. And then if you said, I want actually raw data in a repository and I want them right now, it was only one trial, 2 publications from the same trial that made the data available right away. The others you had to ask, you had to set requests, you had to set a proposal, and some hopefully would be approved. If we can't see the data, how much trust can we put on them? John Carlisle, an editor of Anesthesia, which is a very serious specialty journal, one of the best in anesthesiology, had been asking authors of people who send clinical trials to his journal that he wants to see the raw data from these trials before making a decision on whether the paper should be accepted or not. So he got about 150 trials worth of raw data, and looking at them, he concluded that 30 to 40% of them were so improbable that either they had been completely messed up and therefore entirely unreliable, or very likely they were fraudulent. He called these trials zombie trials, and when I wrote an editorial, which was published on a Halloween day a couple of years ago to accompany his experience, I wrote that hundreds of thousands of zombie randomized trials circulate among us if what he saw in his journal applies to the rest of the biomedical literature. And there's no reason to believe that his journal is seeing worse trials compared to what other specialty journals are seeing. Conversely, in higher trust environments, I think that the reliability of the evidence is much higher, and I think it's getting better and better. For example, BMJ and PLOS Medicine have been asking not only for data statements, but also a precondition for publication is that authors will share their data if they're requested. Otherwise, they will not publish a clinical trial. So we did go to the authors of BMJ and PLOS Medicine publications, and we asked for their data. About half of them did send them to us, 46%. And that was very brave because we told them that we will reanalyze the data. And it's a little bit like getting an audit letter from IRS. But they did send the data. We reanalyzed them with Floriano Det and other members from my team. And we saw that all of them, the conclusions were not affected. We saw some very minor differences in some of the results, but nothing that would shake any of the main conclusions. So in a responsible sharing environment, I think that we can put full trust to the literature. And in fact, there's more and more sharing happening. We have that observatory where we capture what is the percentage of shared articles that share their raw data. And we see a clear increase over the last decade. We have repeated that exercise looking at the entire open access literature in PubMed. And we see that clearly data sharing has gone up from close to 0% in 2000 to about 20% or maybe even a bit more currently. Code sharing is lagging behind a bit, but of course, many articles just don't have code. Protocol registration at about 6% at the moment. Much better disclosures for sensitive aspects like conflicts of interest and funding disclosures. They're almost always there now, while they used to be absent. Of course, we cannot be certain that they're 100% complete and accurate, but I think that that's much better to have a placeholder for stating what the funding and potential conflicts might be, and an increasing proportion of papers that say that what they do includes some replication. This is another view of the same data. You can see the gradual increase on all these transparency indicators across the biomedical literature. Now, these practices are not equally distributed across all science. These are maps of science, and you can see color when these transparency and reproducibility indicators are satisfied. As you see, there's a lot of color for open access, which means that the paper is available open access, and I think this will become even more dominant. For example, Europe has a very strong plan at the moment to make everything transition to open access. But as I said, open access publication is just an advertisement. You need more. You need the raw data. There is color for data sharing of the raw data in some areas of the universe of science. There's also a little bit of color for code sharing, not exactly in the same areas as data sharing, but some overlap. If you go to the bottom right, protocol registration happens in completely different fields. For example, protocol registration is very common in clinical trials, but clinical trials do not share their data very often. And a lot of color for conflicts of interest and funding disclosures, which, as I said, do have placeholders in the vast majority of journals at the moment. Some journals are doing better than others. For example, there are journals at the moment where 75% of the papers that they publish, they have their own data available. And there's even some that almost 50% of the papers share code. But the vast majority are much, much worse than that. I think hopefully we will see some shifting of these curves to situations where we will see more journals being more open and more transparent. We have new challenges as we move to more complex computational methods. We have a very rapid advent of opportunities, but also caveats with the use of complex computational methods like artificial intelligence and large language models. Being transparent and being open with these tools means that you need to say more. If you want to be transparent about a linear regression, you just need to give the coefficients and the constant. But if you have an artificial intelligence with deep neural networks, much more information needs to be conveyed. Many years ago, we published that set of guidelines in Science to try to help investigators to come up with more disclosure about the details, the essential details of their computational methods. And of course, it makes a difference, as I said, if you have a very simple model, linear regression is at the top left of that space, versus deep neural network algorithms that are very complex, but non-transparent unless we make some extra effort. That extra effort is not that onerous, actually. And in fact, with newer computational abilities, we can be very transparent. This is some guidance that we offered in a paper in Nature 3 years ago, where we gave examples of what are the resources that could be used to make even the most complex and most black box looking type of artificial intelligence very transparent, very reproducible, very easy to repeat what has been done. Finally, my closing thoughts are about how do we incentivize people to do all of that? How do we incentivize people to create better science, more reproducible science, science that makes a difference? I think we need to move away from productivity as a sole criterion of what matters. I have nothing against productivity. I love doing research. I love writing papers. I love publishing. If you tell me stop doing research, I would probably go into major depression. So productivity is fine, but it needs to be coupled with quality, reproducibility, sharing, and eventually translational impact of research that includes multiple dimensions. It includes social dimensions, changing our world in a meaningful way, in a way that makes it a better world with more diversity, with more equity, with more inclusion, with more opportunities, with less injustice, with many, many things that can be done about research and its outcomes. So if you run that acronym, it's an electrocardiogram, PQRST, the electrocardiogram of rewarding research and investigation. I think we need to pay attention to all of these different aspects. Unfortunately, if you look at university handbooks, like medical school handbooks, we looked at 92 medical schools and their handbooks of what they say that they will use as criteria to recruit faculty or promote faculty or give tenure. And practically that language is not there. Typically, they just focus on traditional aspects of productivity rather than these more progressive types of features and criteria. However, in my experience, I think that in real life, these additional aspects are taken far more seriously now in most environments, and maybe just handbooks take a while to be revised. Some of them were written in the 19th century, and they're revised slowly. Even the world is changing far faster than that. To conclude, I believe that we need more research, not less research. We need more science, not less science. But we also need high quality reproducible science for cancer, for all sorts of major outcomes, for cardiovascular disease, for any sort of public health. And we need new paradigms. The fact that I showed you examples where research was non-reproducible does not mean that we should not trust that this is the best that we have. I mean, we cannot trust conspiracy theories. We cannot trust just opinions, even opinions for experts, without science. But the reproducibility of many scientific disciplines has substantial room for improvement. There are many possible interventions that may improve the efficiency of research practices and the reproducibility, and eventually the utility of the evidence. Transparency, openness, and sharing are likely to help, but details on how to promote this can be important. And yes, useful research very often remains a largely unmet goal, but we should not give up hope. We have made great progress, and I hope that we will make even more progress in the future. Thank you very much. I hope we do have time for questions.
If people want to unmute and clap, and thank you very much, Dr. Ioannidis. If anyone has any questions, do you want to go ahead?
I could listen to your talk for another hour. I guess you hear this all the time, but there is no money for this, and that's the biggest problem. In my view, the $500,000 cap has been in play from the NIH for my entire career, although the cost of insulin kits is up 4 times. And now we are to hire someone whose job is to upload our data, a full-time position. And we all know that, we all hear that. I have found clinicaltrials.gov to be a complete waste of my time. All it gives me is people calling me or emailing me from Colorado wanting to know if they can be in our study that requires them to be in the state of Missouri. So patients are confused. So I really like everything you said, and I'm looking for ways that we can continue to comply and actually have enough money to test a hypothesis, because we're so busy uploading our protocols and our data that we don't get any science done. I'm that's a statement, not a question, but
I fully sympathize with.
Well, so how do you respond to scientists who say I can't do it? Because I think it's real.
Well, I think that all these efforts eventually they should try to make things more efficient, make science easier to do, more efficient to do, not make it more difficult to do. And unfortunately, many of the requirements, they're not evidence-based. There's a lot of bureaucracy out there. Administrative teams are becoming bigger and bigger. Requests for compliance are becoming more and more onerous. We see that every day, every hour, practically. And very often, these are done in the name of improving reproducibility and reliability. But then no one has really asked people who work on reproducibility and reliability whether all of that mass of requirements is really what would make a difference. So it leaves actually less time, less effort, and fewer resources to really do reproducible research. So I clearly sympathize with that point. At the same time, I don't want to alienate administrative teams and funders and sponsors because maybe they feel that they're in a defensive position, that they need to do something to respond to this, and they just don't necessarily do what is necessary. So, maybe relax and let's look at the evidence and what works and what does not work. We don't want to burden researchers. I mean, it's becoming very difficult to be a researcher nowadays, especially for the younger generation. When they see all the obstacles, they run away. So we want to reverse that. We want people to be enthusiastic, that that's the best thing that you can do, and you can help, and you can make a difference, and it's so fascinating, rather than goodness, you need to do 10 times the work before you start doing the work.
Thank you so much, and for all your comments.
Thank you. Very good nuggets. I've taken a lot with me. Can you give us some practical steps regarding how to deal with non-significant results? You rightly said, like in the literature, most of the published literature is biased towards significant results. So you spend all the time, you get your result, and you're not seeing any effect of your intervention. Does that mean your result is not meaningful? Like, what are practical steps you have for junior faculty like myself?
And non-statistically significant result is as meaningful as a statistically significant result. I mean, it shouldn't have a second-class citizen status in the Republic of Results. And I think that there is a misconception that non-significant results cannot be published. Yes, perhaps they would be less likely to be published in New England Journal of Medicine. Even JAMA has run a study that shows that they don't see any difference in the acceptance rates for significant versus non-significant results. In terms of the information gain, sometimes, not uncommonly actually, non-significant results may be more informative compared to significant results, because they may be refuting, for example, something that we thought was so, or they may be changing our perspective in very major ways, which means that they completely shift the center of gravity of the evidence, what we know and where we should go next, what should be the most meaningful next questions. I think more and more people realize this. I've seen several studies that show that quote unquote negative results can be published if people just submit them. So I think they should just be written up and published. And I think that at the level of reward, I never appraise a scientist as being a better scientist if they have more statistically significant results compared to another. And in fact, if I see that someone has only statistically significant results, I start worrying that there's something wrong here, because the most likely scenario is that most of the results should have been not that fascinating to start with.
Go ahead, Japna. She's written a comment in the chat, but.
Hi, this was an excellent talk, and most of what you said, I'm sure resonated with so many of us, and especially considering what we've been going through recently. Sorry for another time, but there's been this movement in the other sciences, the sciences other than biomedical sciences. You look at the natural sciences and the biological sciences. There's this movement in publishing or pre-publishing research on preprint servers. And in some cases, there's also a very extensive pre-publication discourse, which has resulted in strengthening the post-publication findings. And so what are your thoughts on utilizing that same model for the biomedical sciences?
I'm very much in favor of preprints and similar options. And I'm also in favor of exploring different ways to intensify peer review at earlier stages. You may want to take a look at a paper that I published with colleagues at the Journal of Clinical Epidemiology this month or last month on very early peer review, actually even before the study is done. But then preprints would be peer review or some sort of peer review on a very wide level after the study is done, unless it's a protocol, in which case it could be even before the study is done, for exposure to the wider community. I have supported these efforts, and I'm glad that we do see more of that happening in the biomedical sciences. I think the pandemic also promoted the use of archives like medRxiv and bioRxiv. It gave a clear boost to their visibility. and people became more familiar to what they are and how they should be used. I think that there's still growing pains in terms of what it means and whether these things should be disseminated. They're not vetted yet, and what do you make of them, and how much weight you should put. But I'm in favor of more transparency at different steps. Unfortunately, empirical studies show that most of the preprints do not get any serious comments, and most of them do not really change much versus the final publication. Peer review is overburdened. We all get zillions of requests, and we can only do that much. Almost all of that is done with no remuneration or other benefit to the peer reviewer. It's estimated that we're talking about many billions of dollars of free labor in a sense. The publishing industry is having a market or an annual cycle of work of about $30 billion. They have a 30% profit margin in this, and poor researchers are just trying to do peer review. Most of them well-intentioned, some fraudulent. We have, different sorts of anomalies in peer review. We have mega journals that just publish massively. We have cartels. We have lots of predatory journals. There's not even agreement on what is a predatory journal and how much we should expand the definition. So in principle, anything that can improve transparency and can make things more visible, I'm in favor on. And I think preprints on the balance are a good idea, but they're not a panacea.
Mm-hmm. But I think, preprints provide a great avenue for graduate students and postdocs to strengthen their peer review skills, and also for the authors to get valuable comments. And, traditionally, we have limited participation from graduate students in the traditional peer review journal process. And I think if we were to just encourage our trainees more, and to evaluate these preprints, I think it would help. It's a process, and it's not going to happen overnight, but I think it is a step in the right direction.
I agree. More benefits than harms.
Yeah, thank you.
There's some great comments in the chat. Gavin, you want to moderate them, or?
Yeah, I can read them unless Joshua, do you want to ask? Okay, I'll read it. So there's one question from Joshua, and he asks, do you think the potential solution or step in the right direction is a standardization of protocols and procedures for studies pre-study, or that the solution is a more careful vetting done by IRB or governing bodies?
Very nice question. As I said, I mentioned that paper in the Journal of Clinical Epidemiology, where we say that probably we should shift to earlier steps, that, once you have a completed study, there's not much you can do. I mean, if it's a horrible study, it's a horrible study, no matter how you put it. You can make it more transparent that it is horrible, but it's too late. So anything that can be done earlier, and that could include IRB, that could include some efforts to standardize processes and principles, and make sure that the starting point has a higher level in terms of quality and rigorousness and transparency and potential, then I think that would help. And that would also probably help avoid some of the waste that happens. The counter argument to this is that you don't want to be that too restrictive, because that would mean that many people with ideas that may be considered quote unquote crazy by a majority would not be able to move forward. So you want to keep some of that craziness that may be innovation sometimes, but at the same time, make sure that you give it the best possible shot, and things that are legitimate methods and standards and principles should be adhered, rather than have someone who doesn't know about them and can easily find out that, yes, we have these tools that can be standardized, and you can follow the crazy idea in a much more efficient way.
Okay, there's a couple more questions in the chat. Do you have time? I want to make sure we just...
Of course, yes.
Time. Okay, so there's a question from Dane Jacob, which is similar to a question I was thinking about asking. And he asks, if you were a policymaker or director at the NIH, what would be the biggest one-step change you would make to impact the discussed issues? Any idea why reasonable steps are not currently being taken and encouraged by governing bodies for reproducibility and collaboration, etc.?
Very, very difficult question. And probably it would take me hours and days to try to answer it. I have been in touch with people at NIH, and I have great respect for leaders at NIH, including people who run their funding mechanism. I can see that they don't want to rock the boat too much. I mean, they have something that has been working since World War II, and it's almost a century, with practically no major modifications in the main structure. I mean, it seems like things are changing every month, or at least every year, but in fact, the main structure has not changed much. So saying that overnight this is going to change is not realistic. But I would say that many of these practices have not, at least the best possible research practices have not been adopted, or efforts that have been made are not really necessarily yielding the benefit that we want, and they're adding extra bureaucracy. There's superimposed problems, for example, with difficulties with funding high-risk ideas. There's difficulties with funding investigators at a young age. I think both of those need kind of more brave commitments to lower, for example, the age that we have the first R01 or equivalent for investigator from something like 45, 46 years. I mean, that's really, really very, very disappointing. And also, how do you fund high-risk ideas? How do you move to a model that is closer to something like Howard Hughes, where you fund people to do the best work, and then you follow the robustness of the work and the impact of the work, rather than just fund small projects that need to fit into a bureaucratic framework. So there's lots of things that can be done. But as I said, I don't want to sound as if I know all the answers and that NIH is doing a horrible job. Some people might say that it does an amazing job, and this is why the US has more Nobel laureates than any other country. But Nobel laureates would exist no matter what, regardless of whether science makes 1 unit of progress or 50 units of progress. We would always be finding some Nobel laureates even with 0 units of progress.
Okay, last couple. Kalia Fordham asks, in your opinion, where should the burden of data sharing fall? Should universities house websites or data banks fully accessible to the public? Should it be the journal? Should individual researchers have their own link to their Dropboxes or Google Drives? Which method instills the most trust that the data will be shared, are true, valid, and without error?
I can take any of these offers, and I'm not going to exclude one or the other possibility, because data can be shared in many different ways, and sometimes there's platforms that are very well established and very efficient, and they can be used, and it would be a nuisance to try to reinvent the wheel. And in other times, people need to start from scratch. For example, in clinical trials, now we have many platforms like Yoda and Vivli and clinical data requests and others. So can we have yet other platforms? Sure. Can journals help? Yes, if they want, but typically trying to have localized efforts that would be just tailored to a very small community or a very small set of authors or just one journal, they tend to not be so efficient. I mean, they will be very difficult to generalize. Well, if there's more agreement within a wider community and there's repositories that can be used very widely, I think that this would be preferable. Funders, of course, can make a difference, especially funders that have lots of money. They can have centralized resources where they can say that you need to place everything in that database, and I offer you the curation support that is needed. So I don't want to say that there's just one way to do it. I'm happy if it can be done in any way possible, provided that we get eventually what we want to get. But each of these options needs to be vetted in a very specific scenario and also see what it achieves. For example, now we have statistics about the use of different platforms. We know how much effort has been placed, and we know how much they're used, how much they receive different proposals, what is the acceptance rate for these proposals, what do we get out of these proposals of reuse of data, how much do we learn or we do not learn. So it needs to have also some feedback loop to tell us whether some initiative is functional, effective, making a difference.
Okay, thank you. And final question: why are most publishers demanding much more cost changes regarding research publications?
The simple answer is that they want to make more money. So, and as I said, the publishing industry has a work cycle of $30 billion per year with 30% margin of profit, which is among the highest, if not the highest, compared to any other industry. And some want to make even more money. So I think many journals are just now moving into a new type of generation of massive profit, and it just needs to be revisited on whether really that makes sense. It's a far more complex question, and it's not something that me or anyone else alone can address. I think it's what scientists can do as a community, what funders can do, what kind of arrangements can be made between funders and institutions and publishers. How much of that we deem is acceptable, how much is just profiteering. But I do worry that currently we have some profit models that are completely reshaping the scientific literature. We have mega journals, which I don't want to discredit because I think that they can publish amazing work sometimes, but they're creating a completely different literature. For example, if you take epidemiology, the classic traditional journals are publishing 100 papers per year or 200 papers per year, sometimes 300 papers per year. And some mega journals may publish 20,000 papers per year. Actually, one of them that was publishing 20,000 papers per year was delisted from journal citation reports, which is the impact factor, that that crazy metric. Perhaps now they will not be publishing 20,000 papers per year, but they're big elephants in the room. I mean, depending on what they do, they really shape entire fields in one way or another.
Thank you very much.
All right, I think that's all the questions. So thank you very much, Dr. Ioannidis. This is a fascinating talk.
Thank you very much.
You were very generous with your time.
Wonderful to join you, and thank you for the amazing questions.
Yes, thank you.
Have a wonderful day. Bye-bye.
Thank you.
Bye.